Sequence models like recurrent neural networks and LSTMs are powerful tools for processing text, but they have a strict dietary requirement. They cannot digest raw letters. Before they can analyze a single sentence, every word must be handed to them pre-packaged as a numerical vector. This diagram highlights Word2Vec, algorithm 41 in our series. It is the foundational system responsible for generating those exact numerical vectors. To understand how it operates, you have to imagine stripping away the poetry of human language and treating vocabulary entirely as mathematical geometry. Imagine a space where you can quite literally do algebra on words. Before this architecture, machines treated text as isolated, arbitrary symbols. Word2Vec provided the mathematical bridge that allowed neural networks to map the relationships between words as coordinates in a spatial field. Computers are strictly numeric engines. If you want an algorithm to analyze a book review, every single adjective and noun in that text has to be converted into a mathematical format before the analysis can even begin. The naive way to do this is called one-hot encoding. If your dictionary has 50,000 words, you create an array with 50,000 slots for every single word in your text. You fill the slot corresponding to the active word with a single 1 and leave every other slot as a 0. From a memory standpoint, this is highly inefficient. To store the word apple, the computer is forced to simultaneously store tens of thousands of zeros representing all the words that aren't apple. But the structural flaw is much worse. In a one-hot system, the vector for apple is mathematically equidistant from the vector for orange, and also exactly the same distance from the vector for car. All semantic context is erased. For natural language processing to scale across millions of documents, researchers needed a way to move away from massive, sparse arrays. They needed short, dense vectors where geometric proximity directly mirrors shared meaning. In the 1950s, the linguist J.R. Firth proposed that you shall know a word by the company it keeps. A word's identity is effectively defined by its neighbors. Word2Vec mechanizes this theory. The algorithm drags a sliding context window sequentially across a massive corpus of text, sometimes billions of words long. It isolates a single center word and looks directly at the immediate context words surrounding it. The objective is to compress a gigantic 50,000 word vocabulary down into a dense list of just 100 to 300 real numbers per word. This diagram illustrates the most famous approach to this, the skipgram architecture. In this setup, a shallow two-layer neural network takes that single center word and attempts to predict its surrounding neighbors. These diagrams compare skipgram to the inverse approach, the continuous bag of words architecture, or SIBO, which takes the surrounding neighbors and attempts to predict the missing center word. By forcing this shallow network to repeatedly guess missing neighbors over millions of sentences, the system mathematically reverse engineers semantic definitions. It learns what words mean purely by observing their proximity to other words. This graphic breaks down the mathematical bottleneck. Scoring a word against a 50,000-word dictionary incurs a massive computational penalty. To bypass this, the creators introduced negative sampling, comparing the true context word against a tiny handful of random incorrect words, making training feasible. During these small binary checks, the training loop performs a simple adjustment. It nudges the numerical vectors of true word pairs slightly closer together, while pushing the random word pairs further apart. This scatter plot shows the result after billions of these micro-adjustments. The final matrix organizes the vocabulary into distinct, geometrically separated clusters, with nouns grouping with nouns and verbs with verbs, shaped entirely by their observed roles in the text. This coordinate map illustrates a direct consequence of the training. Semantic relationships are encoded as consistent vector offsets, allowing arithmetic on concepts. Take the vector for king, subtract man, and add woman, and the resulting coordinates land nearest to queen. This plot reveals how this consistency extends to real-world entities. The identical vector offsets connect famous people to related events, capturing relational facts without any explicit human programming. Word2Vec demonstrated that semantic relations can be modeled as physical directions, allowing an algorithm to navigate a vocabulary through pure mathematical distance. By combining a straightforward sliding window with the efficiency of negative sampling, a complex semantic geometry emerges as a byproduct of simply predicting nearby words. The system does have a hard limitation. It assigns only one static vector per word. It cannot distinguish between a financial bank and a riverbank. Both concepts are collapsed into a single set of coordinates. Despite organizing a vocabulary of millions of words into a structured space, the code required to build this matrix is surprisingly compact. Modern Python libraries completely abstract away the complex calculus of negative sampling and sliding windows, leaving a clean, simple API for developers to utilize. Understanding the geometry behind the matrix is the prerequisite to using it properly. With the theory established, we can open the IDE and read the implementation line by line. We start by importing GenSim and setting up our foundational corpus structure as a simple list of lists. The algorithm expects data to be formatted strictly as sentences that have already been tokenized. It cannot process raw paragraphs directly. In this code, we provide 3 toy sentences. The first is a collection of fruit, the second groups vehicles together, and the third contains animals. This list of list shape is exactly what the sliding window algorithm will ingest. It processes the arrays token by token, sentence by sentence. Formatting raw text into these discrete token arrays translates unstructured human language into the precise coordinate inputs required by the neural network. To initialize and train the model, we use a single constructor line. We pass in window equals 5. This defines the exact radius of the context window that slides over our text. Next is min count equals 1. This is a necessary override to prevent the algorithm from discarding rare words. For a tiny toy corpus like ours, keeping every single word is critical. We set workers equals 4 to parallelize the gradient descent process across multiple CPU threads for speed. That single function call is the entire engine. It executes all the heavy linear algebra, backpropagation, and negative sampling completely out of sight. Look closely at that single line of training code. Which 2 crucial hyperparameters from our theoretical architecture are missing? We left out the embedding dimension size and the specific neural network architecture choice. If left undeclared, the library defaults to building a 100-dimensional vector space. It also defaults to the continuous bag of words architecture using negative sampling. Once the function finishes running, every vocabulary word has its trained vector permanently stored inside the model.wv object. By trusting these mathematically sound default parameters, you can instantly deploy an optimized embedding model without manually configuring the complex matrix operations. We can extract meaning from this newly trained space using the similarity method. Let's look at the distance between car and train, and then car and apple. This function calculates the cosine angle between vectors, ranging from -1 to 1. Car and train return a high score. Sharing a context window pulls their representations together. Car and apple lack shared contexts, remaining geographically distant, yielding a low score. Now, a caveat. A 3-sentence toy corpus is far too small to yield stable geometric relationships, but the training API behaves exactly the same way, even when scaled up to billions of words. Because the implementation is so simple, the real engineering challenge isn't writing the code. The challenge is knowing where and when to use this model. Mastery of Word2Vec requires understanding its structural limitations, so you know exactly when its static vectors fail and a newer contextual architecture is required. Language is messy, ambiguous, and famously difficult for computers to process. This geometric mapping enables semantic search. Instead of looking for an exact keyword match, a query identifies documents based on their spatial proximity. A search for automobile easily matches a document about a car because their numerical coordinates land right next to each other in the vector space. And those individual coordinates can be combined. By averaging the vectors of all the words in a document, engineers create a compact, mathematically pure input. This allows text classification models to instantly sort through millions of reviews, emails, or articles based on their overall location in this multidimensional space. The concept even extends beyond language. In recommendation engines, engineers use a twist called Item2Vec. If you treat a user's purchase history as a sentence and individual products as the words, the exact same math clusters related items together, powering the customers also liked features on major e-commerce platforms. This scatter plot shows how clustering plays out with real data. To process the internet, you need speed. The original Word2Vec model processed 1.6 billion words in under a day, a feat that made it the undisputed standard for early natural language processing. It also trains unsupervised. The model learns everything it needs straight from raw, unadulterated text, completely bypassing the need for expensive, time-consuming human labeling. The final output is a set of highly compact, reusable vectors, usually between 100 and 300 numbers per word. These dense arrays act as a warm start foundation, plugging directly into downstream machine learning pipelines to give them an immediate understanding of basic vocabulary. Word2Vec won out precisely because of this raw computational efficiency. It was cheap to train, fast to deploy, and became the pragmatic baseline for the entire AI industry. But that same efficiency comes with a severe architectural compromise. To make the math fast, Word2Vec forces the fluid, ever-changing nature of human language into a single, unmoving coordinate. This creates the one vector per word limitation. It also struggles with the unknown. Novel or out-of-vocabulary words that weren't in the original training data receive no vector at all, which can instantly break a rigid data pipeline when it encounters a new piece of slang. Since the model learns relationships based purely on how often words appear together in its training data, it inherits the statistical biases of its sources. If historical text consistently places specific occupations closer to one gender than another, the algorithm mirrors that pattern, turning societal stereotypes into fixed geometric facts. A static vector guarantees unmatched speed, but it ultimately hits a ceiling when confronted with the contextual, adaptive nature of real human communication. The practical rule for deployment is straightforward. Use classic Word2Vec when your system requires fast, cheap, and static embeddings. But look elsewhere if your dataset is small, or if the exact meaning of your text relies heavily on context. This specific engineering breakdown comes from Imran Ahmad's book, 50 Algorithms Every Programmer Should Know. Breaking the static vector ceiling required a massive leap, designing an architecture where a word's vector dynamically changes position based on the surrounding sentence. Word2Vec established the rule that a word is defined by the company it keeps, providing the conceptual bridge to the transformer architecture, which allows words to analyze that company in real time.